practice, some class discussion. And then after that, they're actually going to do, after segment 2, they're going to actually experience this as an exercise by pulling numbers out of a hat. And I think maybe I can take this hat off now. You notice that this has been the beautiful blue color, so hopefully now I'm recovered and immune from further infection. It's important that the students understand the different states that they can be in the susceptible state, which is green, infected but not yet infectious, no hat on, the infectious state, which is red, and then the recovered and immune, which is blue. And that the students progress through these things one at a time. You may have some questions from the students, exactly what all this means, and I'm sure you can answer them. Once we start sampling with replacement, not all students will become infected. So just like in a regular population, even when a flu like the current H1N1 goes through the population, typically less than half, sometimes far less than half of the total population becomes infected. So even though you might have an R0 of 2 for something like H1N1, you don't have everyone get infected. And so the simulation that we play in simulations 2, 3, and 4 are much more like reality. Okay, when you do the sampling with replacement, it is important that each person who has become, was infected and then was infectious and now recovered, that they put their numbers back into the hat or back into the basket, whatever you're using to generate random numbers for your class. Okay? Because that will show that the exponential growth eventually stops and that disease is over. But since we're doing a probabilistic simulation, I can't tell you ahead of time whether 70% of your class will become infected, 55%, or 95%. It's all a probability distribution. And we will have on our website soon, if we don't have it already, an animated simulation game that's in the computer, and you can simulate this 100 times or 1,000 times and see what the distribution would be if you could simulate it that many times. Obviously, in your 1 hour or 50-minute class, you can only simulate it once, and so you're going to get some number out, like maybe 72% of the students became infected with the herd immunity at 50% and R0 equals 2. The herd immunity concept is interesting, and we develop a little bit more of the math about that in the PDF downloadable file about mathematics. There actually is an equation you can solve that predicts exactly what the herd immunity fraction is for this particular situation, and we have those details in there. It's important that the students understand the basic concept of herd immunity, but again, the issue of the details of the mathematics are not so important. Now about super spreaders. If any of the students are quite interested in this, they can go back and they can see that in spread of typhoid, the spread of SARS in Hong Kong in 2003, even HIV spread, oftentimes there were super spreaders who really accelerated the spread of these diseases at the very beginning. And there's evidence also in flu that there are super spreaders. So an interesting question is, how can R0 be 2? And you could have some super spreaders who could even be at 10. Who could, if they're infected, they might, on average, infect 10 other people. So these are questions that the class might ask, or that you might ask the class. And then you get the issue of averages here. So that would be an average that would be highly skewed. There'd be a lot of zeros in the distribution, and then there'd be a 10 out here with a small probability, and the average still could be 2. So they should know about super spreaders and feel comfortable with that concept. When we just do 0 or 4 with a 50-50 chance, obviously what they're supposed to do is flip a coin ahead of time. If they flip heads, then they're going to infect 4 people. If they get tails, they'll infect 0 people. Now the NPIs, one of the real reasons we have this Blossoms module here at this particular time is that we have a pandemic flu in the world, this new novel H1N1, sometimes called, but incorrectly called, the swine flu. And that causes a lot of concern. And what we want to show the students is that by certain behavioral changes, which we articulate in the Blossoms module, you can reduce the chance of becoming infected. And again, in our mathematical download, we actually developed this into an equation where we can actually separate out R0 into 2 components. The frequency of daily contacts with other human beings, and the likelihood, if one of the 2 of you is infected, that you will infect the other. Now, you can reduce the frequency, as an example, by having meetings over the internet or by telephone rather than face-to-face. And you can reduce that probability if two people meet by doing these behavioral changes, coughing or sneezing into the elbow, and other behavioral changes we talked about, washing hands several times a day for 30 seconds, et cetera, et cetera. So we want the students to understand that human behavior can be modeled mathematically and brought rigorously into these mathematical models, and to show, hopefully dramatically, the results of that. And if a byproduct of this math class is that they go home and they talk to their siblings, they talk to their parents, they talk to their friends, uncles and aunts, and they explain the benefits of these NPIs, these non-pharmaceutical interventions, these behavioral changes, that would be great, because that could reduce for them and their communities the extent of prevalence of the flu currently in those communities. So thank you for considering this module. My email address is now shown on the screen. If you have any questions, please email me directly. I'll try to get back to you within 24 hours. Thank you.